Hello everyone, my name is Yong, and I am a PhD student from Peking University, China. In the post session, my topic is triaxially deformed freely precessing neutron stars, continuous electromagnetic and gravitational radiation. Here is my email address. So, if a rapidly rotating asymmetric neutron star in the Milky Way undergoes free precession, it will be a potential source for multi-messenger observation. First, it will emit continuous gravitational waves which could be detected by ground-based gravitational wave detectors. Second, the precession will modulate the timing signals and pulse profile pulsars, which could be detected by radio or X-ray telescopes. Based on the fact that most previous work are mainly on biaxially precessing neutron stars. So in this work, we want to know how does a triaxially deformed freely precessing neutron star moves, and what physical information can be extracted from gravitational waves and timing signals. Here is the configuration and kinematics of a freely precessing triaxially deformed neutron star. The motion can be separated into three kinds. First is the rotation around one of the principal axes. Second is the precession around the angular momentum of the neutron star. Third is the nutation, which means that the wobble angle theta will change during the precession. We work out the time evolution of the configuration with analytical methods and numerical methods. We also use parameterized description of precessing neutron stars. There are three important quantities. First is obliqueness, second is non-asymmetry, and third is the wobble angle. Once we know the time evolution of the configuration, we can give the phase residual and the pulse-width modulation of pulsars, which are functions of neutron star's configuration, opening angle of the emission core, and line of sight. For the gravitational waves, we use the quadruple radiation waveform. Here is the results of timing residuals and pulse-width modulation. For timing signals, we give the residuals of period and period derivative. We also take the Fourier transformation of phase residual. For small wobble angle case, we use the expansion method and give the timing residuals. For pulse-width modulation, we assume that the electromagnetic radiation is confined in an emission cone with angular radius ρ, and as the neutron star rotates, different cards of line of sight through the cone corresponds to different pulse widths. For large wobble angle case, the observer may lose the emission during precession, and for small wobble angle case, the modulation is much weaker. As for the gravitational wave radiation, with this general formalism, we display both the time domain and frequency domain waveform. Here is the Fourier amplitudes of H plus and H cross. The parameters epsilon, delta, and gamma have been exaggerated for illustration purposes. Physical parameters can be easily implemented. To the second order expansion of epsilon, delta, and gamma, the gravitational waves are mainly emitted at two first order lines and four second order lines. So, first, the radio or X-ray signals and continuous gravitational waves of freely precessing neutron star will provide valuable information about the wobble angle, the non-asymmetry, and the obliqueness of the source, which will imply the equation of state. Second, except the radio observations, in the near future, nicer X-ray timing of pulsars may help to track the precession of neutron stars better. Third, the next generation gravitational wave detectors may detect the continuous gravitational waves from precessing neutron stars. That's all. Thank you.